switch, so I'm not going to stand right here.
Just make sure you speak loudly if you got those.
I will. Okay. So go on my first slide, please. So when I was thinking about this, I was thinking about connections of water because that was sort of how it was presented. So I was thinking about linking what's going on with water on and underground with land use and then the ecosystems that occur there naturally or don't, as the case may be. Now, this picture I put up here is a Google Earth image. I know it's kind of small, but it's a Google Earth image of the land in Orange City. So you can see on this line right here, that's the St. John's River, with that big dark spot up there is Lake Beresford. And so you can see that all of the white areas, that's all houses and stores and parking lots and stuff. So you can see in that picture that probably the majority of the picture is white and not well, in this case green, if we're in color. It was, it's gray now, if we're in color it would be green. Can I have my next slide, please? So I was thinking about starting this with what you could see now if you were out walking around, what you'd see in terms of the ecosystems. So I found this map. Actually right now I can't remember where I found the map. I have the citation somewhere, but I found this map that shows sort of a broad swath of the different ecosystems that are in Florida. And you can see at the top up there, you've got, I know you can't read these, but don't worry about it. The top up there are coastal plain ecosystems, so it's some of the ecosystems sort of spilling down from Alabama and Georgia. And then as you get down into the peninsula itself, you've got on this side where we are, flatwoods. There are a lot of flatwoods in there, mixed in with some marshes and swamps and whatnot. Over here we've got very swampy areas, and obviously down here in the Everglades we've got major swamp. The part in the middle I want to highlight for you is uplands. So if you could go to the next slide, you can see that the uplands occur where there are these ridges. Now these ridges are our topography in Florida. We obviously don't have a lot of topography, but the topography is incredibly important because it's the topography that drives where those ecosystems occur. So in this picture, the black areas are ridges. Now these ridges are 10, 20 feet above the areas in between, maybe 30, maybe 40 at most. So the difference between the ridge and what's in between is subtle, but very, very, very important because of the relationship with the water and then the plants that can live there and then the animals that come with the plants and so on and so forth. So these ridges are the ancient coastlines of Florida. And I'm sure you guys all know at one time Florida was underwater, but it's been, the sea level has been at various heights throughout the history of Florida. And actually if sea level were lower, Florida would be much bigger. So the ridge before the ocean drops out is off as close to the coastline now on the east side of Florida, but on the west side it is way off into the Gulf. So Florida could be much, much larger and has been in the past. These black lines represent coastlines from different sea levels. So at one time, the sea level was where number 6 is. At one time, it was where number 3 is. At one time, Florida was almost completely underwater, and all that was exposed was sort of 4, 5, and 8. So this is where the waves built up the sand and the limestone to make these ridges. Next slide, please. And so because of that, you end up with these distributions of habitats. And what I want to point out here is that all those black dots in this one are scrub. I don't know if you guys have seen scrub, but scrub is on the uplands, very sandy. The plants that live there are real tough, very, very tough. They have small, thick, glossy leaves because to reduce evaporation because the water is so depauperate in these areas because they're on the ridges. Very hot, very, very dry. And this one, this doesn't show up super well, but this one is the distribution of marshes. So in between the ridge areas, we get marshes, and this is swamps. So we get these very subtle differences in topography. In the low-lying areas, we get marshes and swamps. And the difference between a marsh and a swamp is a marsh is grasslands and cattails and stuff, and a swamp is trees with water underneath, like cypress trees and whatnot. And then down here, I don't know how well you can see it, but all these little dots, those are the springs. And if you look at the distribution of the springs and the scrub, it's not that different because the springs occur on the edges of the ridges. The scrub occurs on the tops of the ridges, the springs occur along the edges of the ridges. So this topography is driving where all the habitats are in Florida, is the point I was trying to make. Hopefully you can see that. Next slide, please. Okay, so how is it linked to the water? To see how well it's linked to the water, it's good to look at the anatomy of an aquifer. And we have a very shallow aquifer, as opposed to, say, like the Oglala Aquifer in underlying Oklahoma and Kansas and Nebraska and whatnot. That is very, very deep. It takes thousands of years to recharge that. When they pull the water out, they're pulling out water that's thousands of years old. Our aquifer is very, very shallow. It recharges in days or months, which is both a good thing and a bad thing for us. It's very easy to get to the water, and we think it's very plentiful because it's so shallow, but it also recharges easier. So in this picture, this is sort of a typical anatomy of an aquifer. You can see that we've got a change in topography, subtle, but a change in topography. So we've got upland area up here, lowland area down here. And what I really want you to see, in this upland area, we've got recharge. And so we've got water percolating down through the sand and, in this picture, through some clay, down into the limestone underneath. And it's the limestone that's really the aquifer. The limestone is, if you guys have ever held limestone, it's very soft, it's easy to break. And so it erodes and makes these caverns. And so there are small holes, there's big holes. The ones that we tap for drinking water and whatnot are the big holes, but there's lots of small holes too. And they're all connected in various ways, not necessarily predictable. Like if there's, I'm sure there's caverns under us right now, and I can't tell you that the water's going that direction. It might take a very circuitous path and end up over there. Or it might take a circuitous path and end up over there. But it is connected and the water does move. I went to a talk a couple of years ago, and it was about the St. John's River, but somebody was talking about springs, and we were talking about doing a dye study of into Okeechobee. And I don't remember exactly where this was, but in this particular study, they put dye on the landscape where they knew it would percolate down and measured how long it took to come out in spring, and it was something like 13 hours for 30 miles, just like that. It moved fast. It varies a lot. It could move even faster in some areas, and it could move a lot slower in other areas. Not necessarily predictable from up here. Oh, wait, not quite.
That's right.
So we've got the water percolating down into these caverns, and then in the low-lying areas, we've got it coming back out. So these are the discharge areas. This line right here, called the potentiometric surface, that is, if you sunk a well, how high the water would come up into that well. So in the upland area, it's not going to come up to the land surface. You have to actually pump it out. But in low-lying areas, if you sunk a well right here, the water would come shooting out. Or in this spring, the water comes shooting out because that water is under pressure. Okay? And here it's not under enough pressure that it'll come out into the landscape. Down here, because the land is lower, it's under enough pressure that it'll come shooting out. The other thing I want to point out is that there is obviously a lot of sand. We all know there's sand in our yards and everything, right? So the limestone is covered by sand, but in between the sand and the limestone is this clay layer that they call the intermediate confining unit. And in some places it's thick, and in some places it's thin. If you have water coming through and recharging the aquifer, it's going to be relatively thin where the water's coming through. If you have water coming out, it's going to be thin or cracked for the water to come out, because that where it's thick, the water can't penetrate, either up or down. So you see in this picture where we've got a sinkhole, the intermediate confining unit is cracked. Where we've got this spring, the intermediate confining unit is thin or cracked, and so the water can come out. Now, while it's changing, I'm going to drink water. So this is that same figure I showed you before that showed the distribution of spring, but now I'm going to point out the difference in the colors. So in the dark areas, that intermediate confined unit is thick. And so that it tends to keep the water underground in the aquifer. So for them down here to get water, they have to drop a well, drill a well, and then they can get the water out. But in the area where we have springs, the intermediate confined unit is either thin or absent. So where it's this sort of aqua color, it's thin, our area is thin, and in the white area, it's absent. And so any crack in the limestone, that water's going to come shooting out. So we had two things going on here. Before I put this figure up to show you that it was along the edges of the ridges, but we've also got thin clay layer there. So it makes it easier for the water to come out. So let's link this back to land use. So I was talking about sort of the anatomy and what causes the distribution of these natural areas, but we've got land use on top of it, like I showed you at the beginning, where most of this area has whites, either houses or parking lots or whatever. And I found this figure, although the colors are showing up super well, I found this figure on this website, floridaswater.com. I think this is from USGS, if I remember correctly. And I wish you could see this a little bit better, but all of the areas that show up better as pink are high density people, high usage, high landscape manipulation. So all along here, obviously up along Jacksonville, along the coastline here, we've got a lot of people. We know this already. But what I wanted you to look at was looking at that figure and then looking at this one as well, because all of the areas here where it is red are the high recharge areas. So the uplands, the ridges, tend to be high recharge areas. So all along here, and in some cases, the recharge areas are actually not developed. Like if you look at this one, and this is Ocala National Forest. Ocala National Forest is a good recharge area, and it's protected, so it is showing up as green here. But there's other areas, like this whole area right here, which is along I-75, it's pink. There's a lot of development, a lot of parking lots, a lot of roofs and whatnot. That is also a recharge area. There tends to be a high degree of overlap between recharge areas and buildings. And that is because they're uplands, and in uplands you don't get flooding. Good places to build. Next slide. I also found this one, this is on the Florida Fish and Wildlife Conservation, Fish and Wildlife website. And this is a projection of development in Florida over the next 50 years. So this is supposed to be current, right? And here's our I-4 corridor here. That's what it's supposed to look like, or a projection of what it might look like in 50 years. And what I want to point out is that a lot of this development is in these upland recharge areas. Next slide. Okay, so what's the effect of the land use? So in 2000, we were using 1,486 million gallons per day. It was split about half and half between public supply and agriculture. We have a lot of agriculture, again, we all know that. Most of it is groundwater. The vast majority of the water that we use is groundwater because our shallow is easy to get to, and it's clean. The surface water around here is brown from tannins. We don't want to drink brown water, even if it's not dirty. It's still brown. It's not appealing, so we drink the groundwater, which is easy to get to. But this use is projected to increase by 20% by 2025, and the proportion going to public supply, our drinking water rather than agriculture, is supposed to go up dramatically. Even of that amount, the proportion is supposed to go up dramatically. And what I want you to see on this figure is these circles here are drops in the potentiometric surface. So if you remember back to that figure that I showed you of the anatomy of the aquifer, the potentiometric surface represents the pressure in the aquifer. Higher pressure, higher potentiometric surface. Lower pressure, lower potentiometric surface. And right here, and up in Jacksonville, we've got a huge drop in the potentiometric surface already. If we keep drawing more water, that potentiometric surface drops more. So essentially, you can think of it, although it's not equivalent as the water table, a lot of people know the word water table, it's similar to the water table. So essentially, this is like drops in the water table. Okay? Next slide. And so you end up with situations like this. So obviously these are sinkholes. In this figure, it's showing the sinkhole danger, and so red areas are more likely to get these collapsed sinkholes, which is what these are. There's subsidence sinkholes, which are kind of slow slides, and then there are the collapsed ones. Essentially, in a collapsed sinkhole, what happens is, if you think about that anatomy of the aquifer, there's that big cavern, right? And there's a roof to the cavern. If the cavern is filled with water, the water will hold the roof up. But if you start drawing the water down, there's nothing to hold the roof, and the roof falls in, and then you get a house sliding in. Okay, next slide. So that's one of the consequences, or a couple of the consequences of using the upland areas, developing the upland areas. You get less recharge, you get ground water table dropping, you get sinkholes and whatnot. What about the lowland areas? Well, if you use the lowland areas, if you remember back to the figure that I was showing you about the distribution of habitats, those lowland areas are marshes and swamps. And so you end up with loss of marshes and swamps. This figure is loss in acres of marshes over the last, 50 years, 60 years. And you can see that there's actually been a reduction in loss of marshes and swamps. And actually in the period of 1998 to 2004, there was an increase, but it's somewhat artificial because a bunch of those are agricultural ponds. So they were ponds that were created, and they were, the person who was in charge of the EPA at the time categorized those, I forget, changed the description to include these agricultural ponds, and so it looks like there's an increase, but really there isn't. But what I want you to see here is, yes, there's been a decrease in the loss of marshes, but these are additive, right? So we lost all these, and then these are different ones that we lost. And then those are different ones that we lost. And those are different ones that we lost. So we've been losing more and more and more and more wetlands over time. And the wetlands support the wading birds and turtles and alligators and all that stuff. Next slide. The other consequence to us is that when we develop the wetlands, we end up in situations like this. So you go to an area in the dry season and you see a house, and the house looks lovely, right? But if your house was built in the lowland area, when the hurricane season comes, you end up with your house underwater. So this is the Berry in 2008. It's dry now, but in 2008, it looked like that. Okay, so I wanted to give you a few numbers to go with this. I've thought about this in many different ways. Sometimes I think about it in terms of the river, sometimes I think about it in terms of lakes, sometimes in terms of springs. Since you're so close to Blue Spring, I would call it threats to springs. So the major threats to springs are loss of water quantity, loss of water quality, and then I could talk about exotics, but I won't talk about exotics today. We could talk about the effects on the ecology. So next slide, please. Okay, so what does land use do to water quantity of springs? Hopefully, based on what I just told you, you can kind of take a guess what's going to happen. So if we keep increasing withdrawals out of the aquifer, we're going to have reductions in pressure in the aquifer. If you have reductions in pressures in the aquifer, you're going to have reductions in the amount of water coming out. Right? So these are springs on the Oklahoma River, and these are their current discharges. This is the projected, so this is actually kind of old, projected discharges in 2010, and all of them, with the exception of Glen Spring, were projected to decline. Some by quite a lot. Blue Spring, this is not our Blue Spring, this is what Madison and Blue Spring, was projected to decline by 70%. There are springs that have gone dry because of overpumping. And I don't know if any of you guys have seen John Moran's photos, but he came and talked to the Blue Spring Alliance, I don't remember exactly what it was, a couple of years ago, and he had a picture, I want to say it's White Spring, I think it's White Spring, and he's been taking pictures for a long time, so he had a picture of a friend that he took me. The guy's standing, there's sort of an aqueduct that the spring goes through, so it comes out of its cavern, it's an underground cave, and then somebody built this sort of aqueduct sort of thing. And the guy's standing there, and the water's pouring over his shoulders in the picture. It's a beautiful picture. And then he took another picture like 2 years ago of the same guy, 30 years later, standing in the exact same spot, and there's a trickle at his feet. It was stunning. My stomach dropped I saw the picture. Okay, next slide. Because of these problems, they've set these minimum flows and levels. I don't know if you guys have heard of these, but they're setting them all over the state for different water bodies. So if it's a standing water bottle, water body, it might be a minimum level, or it might be a stage in a river or a spring. Flow would be minimum flow rate. So this is the minimum flow and level for the St. Johns River. They've also set them for Blue Spring. And so the average for Blue Spring, the historical average is 157 cubic feet per second. It went down, and supposedly it's going to come back up to 157 cubic feet per second through management. This is what they say. But the reason I bring this up is because clearly water managers are worried about this issue because they set these. They set them, so they say, all right, historically the discharge ranges between this discharge rate and this discharge rate depending upon season. And so we want to make sure that it never goes below here. We know it's going to vary in this range. We want to make sure it doesn't go below here. And the reason they're doing that is because we are having reductions in discharge like I was describing. Next slide, please. So what does that mean for the springs? Well, you end up with lower gauge heights. You might end up with water stagnation. So if you've got water that was shooting out of the spring and flowing rapidly down the run, and then you reduce the discharge, well, it's going to start trickling instead. The water's going to be lower. It's not going to flow as fast. You're going to end up, you can't see this super well, but this water has a sheen because it's stagnant. There's decomposition that happens in any water body, but it's not flowing away. It's just staying there. So you get oils building up on the surface and stuff like that. Next slide. Okay, so let's look at that's water quantity. Hopefully I've made an argument for how we're having problems with water quantity and what that might do. Let's look at water quality, which is almost as disturbing. Next, please. So you guys may already know the word eutrophication, but eutrophication is essentially overgrowth of algae in response to increases in nutrients. This is a picture from Lake Okeechobee, and Lake Okeechobee has eutrophication problems because of all the agriculture around it. So there's all these canals coming in. I think this is actually right where, I forget which one, but one of the canals coming in that's draining the sugarcane land. And so this, even though this picture isn't showing it great, you can see the streaks in the filamentous algae that's growing there. This should not be this thick. Next slide, please. So you get all these nutrients coming in. What do the plants do with this? So most of the nutrients are either nitrogen-based or phosphorus. If it's nitrogen, they use it to build their bodies. They use it to build proteins, nucleic acid, that's DNA and RNA that all cells have, right? So to build new cells, they need to build protein, they need to build DNA and whatnot. And so they use the nitrogen for that. Phosphorus, which is often a limiting nutrient in a lot of systems, is used again for nucleic acids. ATP is the energy that cells use. It's sort of like the currency for cells. So again, it's used in abundance. Next slide, please. So what do they do if you add a lot of nutrients? They reproduce. So here's a low nutrient lake. Here is a high nutrient lake with an algae problem. If you add nutrients, that algae are happy and they will reproduce and you'll end up with that big green nasty mess. The problem with that is not only that you end up with this big green nasty mess, but the lifespan of an alga is short. It is on the order of days. And so that alga dies and then it sinks down to the bottom, and then you get decomposition down there. So there's bacteria waiting to decompose it, and that's what bacteria do. That's why they're there, right? They're supposed to. But the more organic material you have up here, the more it rains down, the more decomposition you have down here. Those bacteria, as they're decomposing, use oxygen. And so you end up, in this picture, you get the happy crabs crawling on the bottom. Here you've got dead crab upside down because it doesn't have any oxygen. So when that water stagnates and you get all this production, you end up with lots of oxygen and then the critters die. So how did they get there? How do these nutrients get there? In our case, there's two different ways. There's point source pollution and there's non-point source pollution. Point source pollution is what they really started attacking in the late 60s and the early 70s. Point source pollution is when you've got something like a factory or a water treatment plant or something like that that's got a pipe that's dumping the water in, dumping waste or whatever into a river, into a stream, that's really, really obvious and really easy to take care of, right? You say, all right, we don't do that anymore. We route it somewhere else, we filter it, we do something like that. And so we've done that to a large degree. We've stopped a lot of these point source pollutions. The bigger problem is the non-point source pollution, which is diffuse. This is fertilizers across the landscape. Cows, which make their own fertilizer across the landscape, which then runs off in various places, not one spot where you can put a filter, but across the landscape. This is what we have problems with agriculture, with domestic use, fertilizers on people's St. Augustine grass and whatnot. So once the nutrients go into the system, they can, there's a couple of different options. One is they could actually be used in the system by the algae reproducing, and you get the nasty green mess. Or another option is, if you go to the next slide, that they get stored in the system. This is the problem with, one of the problems with Lake Okeechobee and Lake Apauca, if you know anything about Lake Apauca. These nutrients come in, the algae reproduce, they sink to the bottom, and then they stay there in the sediment. And they don't go anywhere. They're not getting flushed out. Our shallow lakes, they don't get flushed like some places do. And so those nutrients just stay there, and when the wind blows, the nutrients come up, you get a new algae bloom. So they could get used, they could get stored and used later, or the last option is they could get transported. And in our case, we're not getting transported to the Gulf of Mexico. We would be getting, these nutrients would be getting transported on down the St. Johns River and eventually into the estuaries around the St. Johns River. But what I wanted you to see here, this is a plume that's coming from the Mississippi River, which transports a lot of nutrients. And so you get lots of big, nasty algae blooms and low oxygen where the Mississippi River enters the Gulf of Mexico. Next slide, please. So I actually just put this together the other day from St. Johns River water management websites, looking at nutrients in a few springs. That's some of the ones we have around here. And what I want you to look at right here while you're thinking about this is eutrophic means high nutrient. So oligotrophic is low, and there's mesotrophic, eutrophic. Historically, most of our springs are oligotrophic, low nutrient. But I put this on here so that you can sort of refer back. And you can see in terms of phosphorus, all of the springs are in the range of eutrophic. In terms of nitrogen, which is what's been increasing over time in a lot of springs, Alexander Spring is still low, Juniper is low. These are in Ocala National Forest, and their watersheds are Ocala National Forest. They're still low nutrient. Delian Spring is up pretty close to eutrophic. Blue Spring is heading that direction, although not really there yet. Gemini Spring is definitely eutrophic at this point. The TDS is total dissolved solids. That's stuff in the water column, which you'll get more of the more algae you have. That when that algae breaks down, then it will end up as sort of stuff in the water. And you can see there's a relationship to some degree with how much nutrient there is and how much total dissolved solid there is. Chloride is, I just put on there just in case you're wondering. The chloride is, it's a measure of how much of the ancient seawater is coming up. Because in a lot of these springs, it's a combination of ancient seawater that's been there a long time and then the shallow aquifer, and so you get a combination of those. Next slide, please. Okay, and then finally, so we talk about water quantity, water quality, and then what does that do to the ecology? And I put this picture on here to show you the difference between a healthy eelgrass bed and what's happening, although this picture is actually in an estuary. I couldn't find a good springs picture with the situation that's happening now in a lot of systems. I know there's pictures out there. I just had a meeting where they were showing pictures like that. I just couldn't find one for today. But here's a healthy eelgrass bed, and eelgrass is great habitat for invertebrates and for fish. Some fish will go in and out, little killifish will go in and use these areas. They'll hide from predators. They eat off the eelgrass because there'll be all kinds of inverts all over the eelgrass. But when we start to get more and more nutrients coming in, we start to get the growth of these different types of algae, especially the filamentous algae. The algae will cover the eelgrass and actually kill it. We have, if any of you guys have been down there, we have exposures that we put in at Blue Spring. There's 3 of them where we planted eelgrass. We planted it, it looked beautiful, it looked gorgeous. A week later, it was blanketed in algae, totally blanketed. I cleaned it off. We'll see if it survives, I don't know. I'm not sure whether it's gonna survive or not. But anyway, so this situation is not good for these guys, for the fish, right? So if you have reductions in water quantity,